This is the title of the analysis, focusing on the parameters of the sparse random projection algorithm used for dimensionality reduction in machine learning. We'll be examining how different parameter choices impact performance and efficiency. The core question. We're using a tool called Sparse Random Projection from scikit-learn, a popular Python library for machine learning, to make a large dataset smaller. The dataset is sparse, mostly zeros, has 10,000 samples and 100,000 features, with an average of 10 non-zero values per sample. The goal is to understand the effects of different parameter choices on efficiency and memory usage when reducing the data to 500 components. This section describes the setup. A large, sparse dataset is being processed using sparse random projection, a technique to reduce the number of features while preserving important information. From scikit-learn, it highlights the dataset's size, 10,000 samples, 100,000 features, and sparsity, mostly zeros. The objective is to determine which statements about the algorithm's parameters are correct when considering efficiency. This is the first multiple choice option. It's a statement that needs to be evaluated in terms of whether setting the dense_output parameter to true, meaning the output is a full matrix, will always be faster than leaving it as false, meaning the output will maintain sparsity. The second option examines whether setting a smaller random_state which controls the random number generator's seed for reproducibility, affects the performance of the algorithm. The third option focuses on the EPS parameter, controls the density of the random projection matrix. It tests the understanding of the trade-off between computation speed. A higher EPS results in a sparser matrix, hence faster computation, and potential information loss. The final option questions whether the sparse random projection algorithm is inherently bad at handling large sparse datasets, irrespective of the parameters chosen. This section introduces the core concept. We're using sparse random projection, a dimensionality reduction technique from scikit-learn, to handle a massive, sparse dataset. Think of it like condensing a huge, mostly empty room, sparse data, into a smaller, more manageable space. We are focusing on understanding how different parameter choices within this algorithm affect speed and memory use. The quiz is all about the trade-offs involved. This describes the dataset's characteristics. Imagine a spreadsheet with 10,000 rows, samples, and 100,000 columns, features. Most cells are empty, zero, but each row has about 10 non-zero values on average. This sparsity is crucial because efficient algorithms exploit this emptiness to save time and memory. The goal is to reduce the 100,000 features down to 500, simplifying the data without losing too much information. It's like taking a blurry photo and sharpening it, retaining the key details while removing unnecessary clutter. This is done using sparse random projection. This introduces the parameters we need to understand within the sparse random projection algorithm. These are settings that control how the algorithm works, affecting its speed and the quality of the result. We'll evaluate their impact on a large dataset. This parameter decides whether the output of the dimensionality reduction is a dense matrix, full of numbers, or a sparse matrix, mostly zeros. Choosing dense_output equals true might seem intuitive, but for huge sparse datasets, it's often inefficient as it involves creating a much larger, dense matrix which consumes huge memory. The random_state parameter is crucial for reproducibility. It sets a seed for the random number generator, making sure the results are consistent across runs. However, it doesn't directly affect the speed or memory of the computation. It only governs the random aspect of algorithm. This parameter controls the density of the random projection matrix. A higher EPS leads to a sparser matrix which can significantly speed up computation. Fewer calculations are needed due to the increased number of zeros. However, increasing EPS also increases the loss of information, which we need to balance. This statement suggests that sparse random projection is inherently bad for memory, regardless of parameters. This is incorrect. The algorithm is specifically designed to be memory efficient for sparse data. This statement is incorrect. This section sets the stage. We're diving into the world of sparse random projection, a technique used to shrink the size of really large datasets while keeping as much information as possible. We'll be looking at how different settings within this technique affect how fast it runs and how much computer memory it uses. Here's the data we're working with. A giant dataset with 10,000 samples, like rows in a spreadsheet, and 100,000 features, like columns. Importantly, it's SPARSE, meaning most of the data points are zeros. On average, each sample only has 10 non-zero values. This is a setting in the sparse random projection algorithm. Means the output will be a full, or dense, matrix. This means that even if the input is sparse, the output will be filled with data, including many zeros. This can consume a lot of memory for large datasets. The randomstate parameter controls the randomness. Think of it like setting a seed for a random number generator. If you use the same randomstate value, you'll get the same results each time. It doesn't change the efficiency. EPS is a parameter that controls how sparse the projection matrix is. A higher EPS value means a sparser matrix, resulting in faster computation. The trade-off is that some information might be lost in the process. It's a balance between speed and accuracy. This statement claims that sparse random projection is always bad with memory. That's incorrect. The whole point of this technique is to be efficient with memory when dealing with sparse data that has mostly zeros. This is our goal, to reduce the massive 100,000 features down to just 500. This is called dimensionality reduction. We want a smaller, more manageable dataset, while preserving the important information. This question explores how different parameter choices in scikit-learn's sparse random projection impact performance and memory usage when dealing with a large, sparse dataset. Understanding these choices is crucial for efficient dimensionality reduction. It's like choosing the right tools for a job. Different tools are better suited for different tasks. Here, we are analyzing the trade-offs of using different parameters. The problem describes a typical real-world scenario involving high-dimensional data where most entries are zero. Think of a very large matrix with mostly zeros. This requires handling and processing carefully to avoid inefficiency. The goal is to reduce the size of this dataset while retaining meaningful information. The objective is to reduce the number of features from 100,000 to a more manageable 500 while preserving essential information. Dimensionality reduction is a common technique in machine learning to simplify data, reduce computation time, and potentially improve model performance by removing redundancy and noise. Imagine trying to navigate a forest with 100,000 trees. It's overwhelming. Reducing that to 500 key landmarks could be greatly useful. This statement explores whether forcing the output of sparse random projection to be a dense matrix, dense_output equals true, is always faster than maintaining sparsity, dense_output equals false. For large sparse datasets, keeping the output sparse is generally more efficient. Converting to dense would fill the matrix with zeros, increasing memory usage dramatically and potentially slowing down computations. Think of it as this. Do you want to move 10,000 very small boxes all filled with air or just 10,000 individual pins? This assesses whether selecting a smaller value for random_state impacts performance. The random_state parameter controls reproducibility, not speed or memory. Choosing a specific value allows you to repeat experiments with the exact same results, but it does not affect computational speed or efficiency. This explores the trade-off between speed and accuracy when adjusting the epsilon, EPS, parameter, which controls the density of the random projection matrix. A higher EPS value leads to a sparser matrix. Thus, fewer computations are needed, which makes it faster. However, more sparsity means some information might be lost. It's a balance, speed versus accuracy. This assesses the inherent efficiency of sparse random projection with sparse datasets. This statement is incorrect. The algorithm is explicitly designed to be memory efficient with sparse data by avoiding unnecessary calculations on zero values. This is like using special tools to handle only the essential parts of a problem while ignoring the unnecessary. Okay, So we're looking at how different settings in the SparseRandomProjection function impact its speed and how much memory it uses. This function helps shrink a massive dataset, making it easier to handle. We're talking about a super big dataset here, 10,000 samples with 100,000 features each. This describes our dataset. Think of it like a giant spreadsheet. Most of the cells are empty, zero values, making it a asterisk sparse dataset. That's key because it means we can use clever techniques to save space and speed things up. Our goal is to reduce the number of features from 100,000 down to just 500. This makes the data much smaller and easier to analyze, without losing too much important information. We're using SparseRandomProjection to do this efficiently. Here, we're exploring if making the output a dense matrix, one where most entries are non-zero, is faster. However, with our sparse dataset, that would fill our computer's memory with unnecessary zeros, making it slower and less efficient. It's like carrying around a whole library of books when you only need one. This parameter controls the randomness in the process. A smaller value just means we'll get the same results each time we run it. It won't make it faster or use less memory. It's like setting a seed for a random number generator. The EPS parameter here controls the density of the random projection matrix. A higher value creates a sparser matrix. This leads to faster computation but may sacrifice some information accuracy. It's a trade-off between speed and accuracy. This option explores whether SparseRandomProjection is inherently inefficient. It's actually designed for sparse datasets. It's like having a tool specifically designed to quickly sort only the important information in a giant box of paperwork. The dataset is large and sparse, containing 10,000 samples with 100,000 features each. Importantly, each sample has only about 10 non-zero values on average. This sparsity is crucial because it impacts how efficiently algorithms like sparse random projection can process the data. Think of it like a really big spreadsheet with mostly empty cells. We want to reduce the number of features from 100,000 to a more manageable 500. What strategies can we use to work with such a large dataset efficiently? This row sets the stage for the quiz. We're considering the choices available in scikit-learn's sparse random projection, a tool designed to handle high-dimensional data, especially when it's sparse. Understanding the role of different parameters will be key to selecting the best approach. Let's examine each parameter separately and see how they affect both performance and memory usage. This question asks us to assess the correctness of the statements regarding "sparse random projection" S parameters in the context of the large sparse dataset. We need to consider both computation time and memory usage when making our assessment. By analyzing each parameter, we can determine which statements are true. Considering the efficiency and memory usage, which statement is most accurate?